Hello, everyone. My name is Liang Hongshui. I am the engineering manager and tech lead at Pinterest. Today, I'm going to talk about Pinterest's exploration of distributed SQL. So the agenda is as below. First, I'm going to talk about storage evolution at Pinterest. Next, I'm going to talk about the Hbase ecosystem that we have. Later, I'm going to talk about the challenges and opportunities we face while we operate the Hbase ecosystem. In the last, I'm going to talk about our initial exploration of distributed SQL database systems. So first, I'm going to talk about the evolution of Pinterest online storage. So this is a rough timeline. Starting from 2012, sharded MySQL solution was introduced into Pinterest. We use this model to store we use this technology to store our core data models, including pins, boards, and users, and we are still using that today. So next year, 2013, Pinterest introduces Hbase into its technology stack, and since then we have been using Hbase as a fundamental building block for a lot of our services, including columnar data store, graph service, for etc. In 2015, RocksDB was introduced into Pinterest, and we use RocksDB we built a number of systems on top of RocksDB, including the key value store and systems for machine learning serving. In 2017, after seeing evolving customer requirements on distributed transactions and secondary indexings on NoSQL databases, the Hbase team started to work on middleware that will be adding these functionalities on top of NoSQL data store. So we developed a number of middleware on top of Hbase to provide these functionalities. Now we're standing in 2020. Is a good time for us to start thinking about distributed SQL. So distributed SQL has been adopting increasing popularity these days. It could well be good fit for use cases that need NoSQL scalability and SQL-like features. So we think that it might be a good time for us to start a serious look into these systems. Before I continue, I want to give an overview about Hbase at Pinterest. So Hbase at Pinterest was introduced since 2013, like I said before. It has around 50 clusters. So we have around 50 clusters at Pinterest storing 10 plus petabytes of data. We have 100 million plus QPS in total, and we have hundreds of use cases that use Hbase-based systems. And you could see Hbase has been a foundational building block for Pinterest infrastructure, and even today, it is still serving in the critical online path. To give you more context about the Hbase ecosystem that we have, first I'm going to talk about some of the systems that were built on top of Hbase, and then I'll talk about some other storage systems we have, in addition to those built on top of Hbase. So speaking of systems built on top of Hbase, we have the graph database, which is built with Hbase and Memcache. We also have columnar data store, which we call UMS, that is built on top of Hbase plus Memcache as well. As I mentioned before, we built several middleware systems on top of Hbase to provide additional functionality. Here we have distributed transactional database built on top of Hbase plus Omid. So Omid is an Apache software that provides a transactional processing layer on top of NoSQL data store. And we adapted Omid into our production use case and made it more scalable. Last, we have index data store, which is based on Hbase plus Muse. So Muse is our in-house search engine that you can think of as a variant of Elasticsearch. So we use the combination of Hbase plus Muse to provide indexing capability for our systems, but we are only providing eventual index consistency using Hbase, using a Hbase CDC system that we built in-house. In addition to the systems built on top on Hbase, we also have other storage systems at Pinterest, of course. I'm not going into detail for each one of them, but just for completeness, we also have, for example, KV Store built on top of distributed RocksDB. We have analytics database that is built on top of Apache Druid. We have time series database built on top of Goku, which is a in-house time series database engine. To summarize, to give you an overview of the architecture of the Hbase ecosystem, here is a graph. At the center of the graph, you see Hbase as the storage repo for all of these systems. On top, we see a list of services that are actually use Hbase. For example, we have the graph database, we have the columnar store, we have the transactional manager for distributed transactions, we have this secondary indexing data store. The right picture is the Muse, which is the search engine that we use for providing the indexing capability. So if you look to the bottom right part, Hbase streams the CDC into a system that we call Hbase Replication Proxy. Effectively, it is acting as a fake replication peer for Hbase that can be horizontally scalable. It pulls those change data from Hbase into Kafka, and we have a downstream consumer called Argus that consume these change logs and use that to feedback into our systems. So after giving you an overview of the systems that we have today, I want to call out some of the key challenges that we have with our existing systems. So the first challenge that we face is limited functionalities. As you could probably tell, Hbase is very powerful after having been released for about 10 years. However, its interface is relatively simple. So it provides a columnar interface, but the primary interface is still relatively like a KV store. So it really limits how you can query the system. So over the years, we have been adding Lego pieces into the system to satisfy evolving requirements. The second challenge is about high complexity. And this is partially related to the limited functionality I mentioned above and the Lego pieces we have to add over the years. The high number of systems and the high system complexity actually leads to high KDO load and onboarding cost. So, and not to mention that Hbase itself has many components and dependencies. So it is actually very challenging for us to operate this many systems in production and maintain Hbase, or tens of Hbase clusters. The third challenge is data inconsistencies. As you could tell, Hbase does not provide transactional support. As a result, while we use Hbase as the building block, various kinds of inconsistencies can arise. And as a result, our clients have to deal with those inconsistencies themselves. Although we explicitly told our customers that the only consistency level that we provide is eventual consistency, sometimes they still find it hard to code against this consistency model, and we have to spend a lot of time trying to debug the consistency issues. The last issue is tail latency. As you could probably know, Hbase is written in Java, and sometimes garbage collection overhead can require heavy tuning. To give you a case study, we have so I'm going to give you an example about Zen, which is our in-house graph database built on top of Hbase. So Zen is inspired by Facebook's Tile system, and it provides fairly basic graph operations like like CRUD operations for nodes and edges. It also provides indexing operations such as unique, non-unique indexes. It also supports Edge queries, Edge local indexes. So these are the most basic operations provided by Zen. It's actually relatively simple as compared to other graph databases because it traded off performance and scalability over consistency and transactions. So the major pain points of Zen is that due to lack of transactional support, various inconsistencies could arise. For example, when you update an index of a particular, when you update the property of a node, it's possible that the update to the node itself succeeds, but the update to the corresponding index failed, as a result causing an index inconsistency. To solve these kind of issues, we developed a separate system called Dr. Zen that will run a daily job to fix all these kind of inconsistencies. Even with that, you have 24-hour time window to wait until the inconsistency to be cleaned up, which can still be confusing for some of our customers. The second point is that Zen needs to maintain separate tables for indexes. As a result, the application logic in Zen itself is more complicated because we have to manage all these indexes ourselves, and sometimes we even need to try rollback operations in case of partial failure, and it just becomes cumbersome over time. Another pain point with Zen is that index backfilling can only be done offline. For example, if customers, they wanted to add an index after they created all the data, they have to wait until 24 hours for Dr. Zen to backfill the data for them. And this cannot be done immediately after they bring up the request. So how could we solve these kind of issues? We started to ask ourselves these questions because our customers really think that these are some of the major pain points that we face. So would distributed SQL be a good solution? So we started asking ourselves, what do we really need? And the answer seems to be that we really need a unified storage backend that provides this NoSQL scalability like Hbase, but at the same time provide the SQL-like rich functionalities so that we can express various kinds of queries against the database itself. That means we can use it out of the box, and we do not need to add complicated middleware on top of the system and use it for satisfying the evolving customer requests. In addition to scalability and rich functionality, what else do we need? Of course, we also need high reliability in production, because Hbase is used for online serving. We require it to have high availability and short mean time to recover. In addition, we want the system to be able to provide tunable consistency. That means it'll be best if the system can provide an option for strong consistency with distributed transaction, while at the same time, for use cases that opt not to have strong consistency, we have the option for them to go with eventual consistency. In the last, we want to provide good performance for sure for our customers, right? We do not want any performance regression for existing applications. So these are the basic elements that we were looking for new storage solution. And given all these properties that we are looking for, distributed SQL looks like a good fit, right? So the exploration actually began. To give you more context, before we delve into distributed SQL world, we actually evaluated around 15 or more technologies. And this include in-house systems, open source technologies, and cloud solutions. We looked at all these systems with many dimensions. So in addition to scalability, performance, all these things that I mentioned in the previous slide, we also considered the operational cost, the migration cost, the programming language, the community support, and cost efficiency, and many other dimensions while we were doing this evaluation. So we looked at these in-house systems, open source technologies, cloud solutions, and we were thinking which ones are the best fits. And it turns out open source NoSQL systems stand out. And these systems include UKBDB, CockroachDB, and TiDB. So these days, people seem to have the increasing interest in these systems that are inspired by Spanner, but without a hardware that provides the true time. Okay, so we went, because the team has limited engineering resources, we can only dive into one system at a time, and UKBDB seems to be a promising system. So the team did a deep dive into UKBDB. We started by performance benchmarking so we did an initial performance evaluation on 3 cases. The first case is KV accessing. We also did indexing and distributed transactions. The overall results look promising so far, and we, in parallel, after the initial performance evaluation of performance benchmarks, we actually started dark traffic with some traffic from production use cases. And I want to note that this is still a work in progress. We haven't made a decision yet, but this is still something that we are actively exploring. So in order to get UKBDB to run in with dark traffic, we designed a schema to be backward compatible with existing application, basically added a new storage backend using UKBDB for our existing systems. We also designed online data migration and validation pipelines so that we can migrate data and validate that they are correct. Now, we are using experimental use cases from the graph database and its index data store to see how it works. And I will probably have more data to show, more updates to share later, because this is still something that we are actually working on. So what is our long-term vision? As you could see in this graph, like on the left side is what we have right now with Hbase ecosystem. Is it possible that with distributed SQL, we can consolidate all these systems into a unified storage service? Let's just call it a structured data store. This service may expose different APIs so that it can work like a converged database. For example, it can provide various data models like table model, graph model, or even document model. Under the hood, we can have a distributed SQL database sitting in there. With the change data capture feature, it can also stream the change logs into a stream process system like Flink. So we can see that with a distributed SQL system, we can potentially get a much simplified architecture on the right. Other potential benefits also include improved consistency or even better performance in some cases. Of course, introducing a new technology involves non-trivial risks and concerns. So we also need to treat this seriously. And these are several main areas that we keep an eye on while we evaluate the system, while we continuously evaluate the distributed system, SQL systems. The first one we want to see is system maturity. But it is understandable that distributed systems, SQL systems are relatively young, like including UKBDB. So we are still exploring to see how mature these systems are, how they behave in production. Another dimension that another potential risk is the migration cost, because currently all our data resides on Hbase-based systems. So it is a very high cost for us to migrate all data and client APIs to a new storage service. Especially this needs to be done without any downtime, so it can be very challenging. The third risk is reliability at scale. So this is still something that we need to further verify, because for now, the performance benchmarks have been done in relatively small clusters. We need to see how the system performs at scale. The last point is operational load. This is also critically important because operating Hbase is definitely not easy. We wanted to see how introducing a new storage technology can help alleviate this load. At this point, it's still unclear because we have no in-house expertise. So we wanted to, this is also an area that we want to keep an eye on. So overall, we are super excited about the opportunities with distributed SQL. These systems come out in recent years, and we are start to see active community engagement in these systems, and people are really leaning towards migration some of their systems into these distributed SQL systems. At the same time, while we are still actively exploring these systems, I also want to share some early learnings that we have so far. So the first learning is that one size fits all is unrealistic. Basically, while we were trying to consolidate everything into distributed SQL, it's probably not super realistic because not all use cases need distributed transactions or strong consistency, but it is indeed important to provide options so that when they need strong consistency or distributed transactions, it is available for them. Another learning is that some use cases might just not be a good fit for distributed SQL. For example, some use cases may have a whole lot of indexes. They need to have a lot of ad hoc query using different combination of indexes. Sometimes using local index or even search engine would be a better fit for these use cases. Another thing that we learned over the dark traffic experimentation is that dark traffic is very different from benchmarks. So for benchmarks running, everything went smoothly and fine, but for dark traffic, we actually needed quite some configuration tunings to get things right. We also realized that low cardinality indexes may create hotspots sometimes. And I want to take this opportunity to give a huge shout out to Hbase team for actively helping us and proactively providing support whenever we need them to push forward this progress. So that's all for my presentation. Any questions?